Thank you very much. Hi, everyone. I'm Leonidas from Barcelona Supercomputing Center. I'm senior researcher there, and I'm also a member of faculty in the Polytechnic University of Catalonia. The work I'm going to present is the master thesis of my student, Cristina Peralta, who did all the work, and I'm just presenting. So this is the outline of my work. We will start with introduction and motivation of our work. We will check a bit of background. We will discuss software porting, experimental setup, the evaluation we performed, and conclude the presentation and present our plans for future work. Our work is focused on safety critical systems. These systems are used in avionics, automotive, and aerospace industries. And they have to be correct, and also their execution has to be within certain time bounds. Any malfunction in the code or programming error in these systems can harm human lives. And traditionally, they rely on very old and simple single-core processors, which cannot provide the performance which is required for new advanced functionalities. Let's give you some examples. From the automotive domain, now we have a lot of cars incorporating advanced driving assistant systems, or ADAS in short. For example, we have autonomous parking, heads-up displays, and even smart mirrors. Nowadays, there are a lot of proposals to remove the actual mirrors from the car and even have camera feeds and removing obstacles and providing full view to the driver. So this simply cannot be done with the existing automotive processors. Similar needs are also in avionics. 2 years ago, Airbus started the first test flights of their automatic taxi takeoff and landing project, in which they did all these operations in a plane without human intervention. And also in automotive, nowadays, all companies work towards fully autonomous cars, which obviously will need a massive level of performance. In space, we have also similar needs. Some years ago, ESA had FISAT, the first demonstration mission, which was launched in 2020. It was relying on AI accelerator. It used Intel Movidius Myriad 2 vision processor. And it was the first space mission demonstrating the use of AI for Earth observation on hyperspectral images. Another similar demonstration mission from ESA was OPSAT-1, which was launched 1 year earlier. And again, is based on COTS hardware. It's using an Intel Altera SYCLCON SoC, which combines a multi-core CPU and an FPGA, and has demonstrated also several high-performance applications on board satellites, including AI. And currently, ESA is working on the next generation missions, FISAT and OPSAT-2. As I mentioned earlier, legacy hardware used in these safety critical domains cannot provide the required performance. So all these domains are looking on hardware candidates that can provide the performance they need. And one of the most promising candidates are embedded systems on chip, which combine multi-cores and graphics processing units. Here you can see some examples. For example, Renesas was one of the first companies introducing SoCs with multi-cores and GPUs certified with ASIL-B, according to the functional safety standard, which is used in automotive, the ISO 26262. Recently, we have NVIDIA, which has designed NVIDIA Xavier and Orin, which are both certified for ISO 26262 for ASIL-D, which is the highest criticality level in automotive. And we also have ARM, which has introduced a series of IPs, both at CPU and GPU, which again are compliant with ISO 26262. And for these reasons, these platforms are very attractive for using safety critical systems. Apart from the performance need, in these domains, we also have, we need not only to use high performance, which can be provided by multi-cores and GPUs, but we also need to program them in an easy way. As I said, automotive, in the automotive domain, we have various criticality levels, which are assigned to different functionalities in a car. And those are known as automotive safety integrity level, according to the ISO 26262. And in the highest level, ASIL-D, software needs to comply with certain rules. For example, restricted use of pointers, no dynamic memory allocation, static verification of program properties, resilience to faults, and fault propagation. However, this is violated by all existing low-level parallel programming models. Fortunately, Kronos has a long history on working on APIs which are friendly for safety critical systems. Here you can see a slide which is very similar to the one that Michael presented in the morning, and shows the evolution of different Kronos APIs. And we can see that we have several safety critical ones. Starting in 2005, we had the first OpenGL safety critical. In 2016, the OpenGL safety critical version 2 was ratified. We had also recently in 2019, the OpenVX subset for safety critical. Last year, it was a great milestone with the introduction of Vulkan safety critical. And for the last year, we have been working with SYCL. We had an exploratory working group about SYCL safety critical. And in fact, last month, we were promoted to a full working group, and we will be working towards the definition of SYCL safety critical in the next months. So this work, it was like a motivation for us to show that SYCL, actually to study whether SYCL it's good for safety critical systems, and promote its use, and also to perform a comparison with other parallel programming models on a candidate embedded platform, and at the same time assess the programmability trade-offs that arise. Since we wanted to do this work and it was related to safety critical systems, the obvious problem we had was the selection of the software to use in order to perform our study. We focused on two domains in aerospace and automotive, and we had a set of requirements. We wanted the software to be computationally demanding so that it could benefit from the acceleration of multi-core and the presence of GPU. We wanted the code to be representative of the type of processing that takes place in safety critical systems. We wanted also to have implementations already available in the programming models that we are comparing with, namely OpenMP and CUDA. And ideally, that software had to be open source so that we can promote reproducibility. Unfortunately, to our knowledge, the only available software that meets all these criteria was software that we previously developed at BSc in our group that focuses on safety critical systems. One of them is called GPU4S benchmark, or it's also known with the name OBP-mark kernels, and focuses on the aerospace domain, and a pedestrian detection application, which is representative of automotive. And now let me talk a bit briefly about background on this. The GPU4S benchmark, it was software that we developed within the GPU for Space project that I coordinated started in 2018. It was funded by the European Space Agency, and we were collaborating also with Airbus Defence and Space in Toulouse, France. And the idea of the project was to investigate the applicability of GPUs for embedded GPUs for space missions. So first, we had to study the feasibility and the benefits that can be brought by embedded GPUs in space applications. So this required to study existing flight software and whether it can be accelerated with GPUs. We had to benchmark different embedded GPUs and also implement a demonstrator of a space use case on an embedded GPU. The problem that we faced was that there was no benchmark for space at that moment. And the reason for this is that space is a very particular domain. It's dominated by proprietary code and export restrictions. So no code could be shared. For example, even if we had a partner in the project that develops flight software. Also, there are no GPU benchmarks for critical systems. Everything that is available is only focusing on high performance computing. So for this reason, we created an open source benchmarking suite, which we call GPU for S benchmark. And the definition of this benchmarking suite was based on a software survey we performed with Airbus Defence and Space across all the domains of flight software that they have in the company. We identified algorithmic building blocks which are used in all of those domains. And then by creating small kernels, we could cover rapidly a lot of different domains. This is licensed with an ESA GPL version 3 like license, and it's co-hosted also with another benchmarking suite that was follow-up of this work. And instead of only application kernels, it implements full space applications that again are open source and representative of the type of processing that happens on board in onboard systems. And both these benchmarking suites now, they are the official benchmarking suites used in ESA. Their use is required in the new projects, research projects that are started and are funded by ESA, and also for internal projects in order to identify what type of applications, what type of hardware is going to be used in future missions. The name is a bit misleading because we started this within the GPU for Space project, so focusing only on implementations on GPUs. But since this evolved in OBP Mark, we have created, ported them in also other type of programming models. We have OpenMP, and also we have sequential versions, verification data. So it really can be used not only for GPUs, but all the type of devices that are candidates for future space missions. And for this work, we received the HiPeak Technology Transfer Award in 2021. Here you can see a high-level point of view of the different building blocks that we have in the benchmarking suite and the different space domains that we cover. We have compression, vision-based navigation, image processing, neural processing, and digital signal processing. We have sequential reference version and 3 types of parallel version. We have a naive implementation that is the most straightforward implementation that we can have, an optimized version, and also, when applicable, we use a version that uses vendor optimized libraries. And the reason for this is that we don't use it only to evaluate performance, but also performance productivity. In particular, knowing how much of performance we can get depending on the effort that we spend, and using as an upper bound the optimized performance that can get the performance that we can get with vendor optimized libraries. And as I said, we had different programming models. We had CUDA, OpenCL, HEAP, and OpenMP. And as part of this work, we added also SYCL. So our contributions in this work with respect to this software was the implementation of these benchmarks in SYCL. We targeted both unified shared memory and buffers SYCL memory models. Again, we had a naive and optimized version, and we followed exactly the same organization so that all our developments will be integrated in the official benchmarking suite. Our code is also released as open source. And yeah, as I said, it's going to be merged in the next version. The other software that we used, it's pedestrian detection. Again, that was an open source application we developed at BAC and UPC. Actually, we developed that back in 2013, before even using a GPU in a car was considered. People at that moment were not believing of using GPUs in the automotive market. And I can't imagine how things have changed. And we developed this as a multi-CPU, multi-GPU benchmark for automotive systems. It was evaluated at that moment in high-performance server class CPU and GPU system, and we got 88 times speed up over the sequential version. Actually, we managed to make it run real time. And we ported this to the NVIDIA Xavier, and it's used also as a research use case demonstrator in the up-to-date Horizon 2020 project in which we participate. This application performs detection of humans in camera images, and this is necessary functionality which is required currently for the implementation of the automatic emergency braking, which is a mandatory feature since last year for all vehicles sold in European Union. Our algorithm is based on a classic vision algorithm, the Viola-Jones method, instead of deep neural networks. And although this provides lower accuracy, it has the advantage that it's explainable and it's easier to be used in a certified context, at least with the current certification framework. And the original application was written in CUDA and was hand optimized in order to achieve high performance. Our contribution in this work with respect to this software was porting it to SYCL. Again, we implemented both memory models, the unified shared memory and buffers, and we had 3 different implementations. A naive one, an optimized version using in-order queues, and a more optimized version using out-of-order queues. Again, our code is open source and is going to be merged with the original application repository. Now let's talk a bit about the experimental setup. We have used 2 different platforms. The first one was a high-performance platform. That was our initial target. We used it mainly for development because it was much easier, compilation was much faster, and also because it was the platform that we knew from the beginning of the project that will support SYCL out of the box. The other more interesting platform was an embedded GPU platform, the NVIDIA Xavier. This is as one of the candidate platforms for safety-critical systems. Actually, in the GPU4S benchmark for the GPU4S project I mentioned earlier, it was the GPU that we benchmarked and provided the highest performance. And in the beginning of the project, we didn't know whether it would support SYCL. Actually, I'm very happy that I've seen today earlier some presentations that confirmed also the same, that we can use SYCL. And as we will see, we use different implementation, which is very promising. And I would like also to try the one that you have used. Now let's see a bit of more of details. The high performance platform is an AMD Ryzen 7 with 8 cores and 16 threads, and an NVIDIA GPU 1080 Ti, Ubuntu LTS, supported CUDA, OpenCL, and OpenMP, and we added HEAP SYCL, which we compiled from source. For the embedded platform, we have an 8-core CPU with 8 streaming multiprocessors in the GPU. And this platform is certified for ASIL-D for ISO 26262. And it was also the main platform that we have used in the Horizon 2020 up-to-date project. And as I said, the winning platform from the GPU4S project. As we have seen also from the previous presentation, there are different power modes that we can limit the power consumption. Our limitation was that we had to select something that did not exceed the 15 watts, because in space there are several thermal issues. In space we cannot use active cooling, so that was we had to reduce the consumed power. Again, the software, it's the same with the one that we have in the high performance platform. It supported CUDA and OpenMP. And we compiled SYCL from source. No difference from what we have done in the high performance platform, and we haven't encountered any issues. So now let me talk a bit about our conclusions regarding programmability working in these use cases. Regarding SYCL buffers, it's the easiest solution when we start a project from scratch, because the programmer doesn't have to worry about data transfer on dependencies. It has lower code complexity, which is something very important for safety critical systems certification. It uses less lines of codes compared to our USM implementation. However, when we have an experienced programmer with low-level GPU programming models, it doesn't offer any programmability benefit. Talking about the unified shared memory, one of the peculiarities is that it uses pointers and dynamic memory allocations, whose use is discouraged in safety critical systems. However, it has a major advantage compared to low-level GPU programming models, which also use these features, which is that we can have automatically computed indices, like in parallel 4, which makes the generated code correct by construction. It's because one thing that we have seen in GPU computing is that a lot of errors come from the way that the programmer computes manually these indices, and for this reason, it reduces the programming mistakes, which is good for safety critical systems. The line of codes compared to low-level programming models, it's similar, so we don't gain something on this aspect, but it provides a good trade-off between the performance and the programmability for safety critical systems. Here we have some results with the GPU4S benchmarks. I don't know how much time. Yeah, we are short in time, so I will not go into the details. I will just tell you that results are as expected. So the USM provides a better performance than the buffers programming model in both platforms. And regarding the performance we get with OpenMP, in some cases it's equivalent, in some cases OpenMP it's faster. And regarding GPU, we have seen a similar observation. Here the USM is much better than buffers, and the performance we got in many times was similar to the CUDA performance. Something that is very interesting and I would like to highlight is that, as I said, we have also versions with libraries. So we compared for certain sizes, matrix multiplication and FFT. And something very interesting was that for the FFT, in all the cases, for the size that we have tested, the performance we got was better even than the vendor optimized library. Now let's talk briefly about the pedestrian detection results. Here on the right, we have the results on the high performance platform. Since we have a pedestrian detection application based on camera, our goal was to meet 15 frames per second. which was already achieved by the original version of the application. Our naive implementation was not able to meet this. Within order, we went pretty close within order queues, and once we applied the out of order, we managed even to exceed the performance that we had with a hand-optimized code in CUDA. However, if we look on the left, on the embedded platform, here we didn't have the benefit. Actually, here there was a 10x difference between the hand-optimized version and the SYCL. So this is something that we have to investigate and find out why. But at least the results we got in the high-performance platform were really promising. And we believe that this can happen also in the embedded platform with some, if we find the problem and we fix it. So our conclusions are that we ported, as we said, this software, the safety critical software to SYCL. We compared performance with OpenMP and with CUDA, and we evaluated this in an embedded platform. Our work confirms that SYCL is a suitable programming model for safety critical systems. It requires less code than low-level programming models for GPUs, requires significantly less effort for the development. It's a less error-prone high-level abstraction and provides a good trade-off between programmability and performance. And we can confirm that the current work that we are doing in Kronos in the SYCL working group, it's a step towards the right direction. As future work, we would like we have some ideas. All the porting was manually performed, so we would like to use the DPC++ compatibility tool and compare with our implementations. Would like also to use other SYCL implementations like the DPC++, investigate the problem that we found for the Xavier, and compare also with other programming models like OpenACC. In Christina's thesis, you can see some preliminary comparison results in the link I provided. Also, from ESA side, we would like to port the full applications to SYCL, and currently I'm coordinating a Horizon Europe project, which started in January. We are going to have a RISC-V based platform with multi-cores and an open source GPU, and we will explore also the use of a preview of SYCL Safety Critical. And I would like to acknowledge our funding agencies, and I would like to thank you for your attention, and feel free to ask questions. Thank you.
Is there any questions? Yep.
Hi, really good talk. I just wanted to know if you used, for the FFT comparison, were you comparing different libraries or handwritten FFT kernels?
We have compared against FFT,
and
the one from NVIDIA.
And what SYCL, and were the SYCL kernels in handwritten?
For the SYCL, we have used the heap SYCL generated code from our optimized SYCL code.
Okay, okay, thank you.
Welcome.
I'm curious, what was the performance of OpenCL? Because you mentioned at the beginning, but we didn't see it in the result.
Yeah, OpenCL we haven't used. I said that it's available in the GPU4S benchmark, but Xavier only supports CUDA. That's why we have used only that.
With the Xavier platform, you're able to use the same memory because they only have one memory, right? So were you able to make use of that in SYCL at all, or is it something that you only use in CUDA or not at all? Or, like, did you move the buffers around always, or did you?
Yeah, always. Very good question. And yes, always we move. We perform copies manually, so we don't use the feature of unified memory from CUDA, just because we want to have full control. So one of the things that in safety critical systems, we need to have full control of the applications. And for this reason, unified memory is like a closed implementation from NVIDIA. We don't know how it works, so better if we avoid it.
Okay, with that, we'll thank our speaker. Thanks for the talk.